In this example, we are introduced to combinations. Now, sometimes students are confused on when exactly they should use a permutation for a particular problem or a combination. A permutation uses an ordered arrangement of items. So, for example, if I have the letters A, B, and C, to permutate those letters, I would have ABC, ACB, BAC, BCA, CAB, and then CBA. And there's 1, 2, 3, 4, 5, 6. So that becomes 3 factorial. And 3 factorial is a permutation. It could be written as 3 permutate 3. Now, for a combination, on the other hand, the order of these letters is irrelevant. I'm just going to write it up here. Order is irrelevant. And what that means is that ABC is the same as ACB or BAC or any one of these, because all that really matters is the group, is the collective. So these are considered all the same. So I often tell students that the reason we call it a combination is because we're combining a permutation with a permutation of non-distinct items. So the formula for a permutation, we have N permutate R. Don't forget N is our number size. R is how many we're selecting. And of course that's N factorial over N minus R factorial. A combination is written similar. It's N, and then we have this C for combination. Now, I'm old school, and when I was in college, we used to call this choose, N choose R, and I like using that because often we will see the word choose or select in a problem, and it helps lend clarity as far as the approach we should take. So I'm going to be calling this N choose R. So N choose R, that's going to be N factorial, just like it is right here for the permutation. N minus R factorial. But similar to non-distinct items, when we had the word Antarctica and we had repeats of the letter A, we had to factor those out of here. Same way with here. We cannot tell for a combination the difference between ABC and ACB because all that matters is the group. So we have to factor that out of there, so we put in R factorial. So the equation for a combination, that's N factorial over N minus R factorial, similar to a permutation, but then we introduce non-distinct, and we go ahead and we then factor out another R factorial. So for this example, it states, suppose your school's cafeteria is having a lunch special. Any 3 toppings on a personal pizza for $5. There are 5 toppings to choose from: green pepper, black olive, onion, pepperoni, and tomato. And of course, we have these 5 questions here. So A says, how many different types of pizzas can a student order with no toppings? Now, as you do any of these word problems, especially as we continue on in this chapter, it's always good to take a nice, clear, logical approach. I mean, the math will work, but of course we should also know exactly what's being asked. So when you think about it, for letter A, it says how many different types of pizzas can a student order with no toppings? Well, logically, there's only one way you can do that, right? Just don't get any toppings on it. But we'll go ahead and we'll do it mathematically. So I'll put A right here. So I've got N choose R. And if you look at this problem here, any 3 toppings on a personal pizza for $5, there are 5 toppings to choose from. We even have that term choose in there. So it kind of lends to what process we should use. So I have N choose R. That means 5 toppings, and I'm choosing none. That becomes 5 factorial. 5 minus 0 factorial times 0 factorial. And don't forget that 0 factorial is equal to 1. So this is 5 factorial. 5 minus 0 factorial is 5 factorial. 5 factorial over 5 factorial is 1. Anything over itself is 1. And of course, we figured that out logically. So we confirmed our logic. We're going to do the same for B. How many different types of pizzas can a student order with 1 topping? Well, if we have 5 separate toppings, green pepper, black olive, onion, pepperoni, and tomato. How many different types of pizzas can a student order with one topping? Well, logic should tell you that's 5. If I have 5 toppings to choose from, if I only want one on there, there's 5 different types of pizzas. But of course, we'll go ahead, here's B here, we'll go ahead and we'll do it mathematically. And choose R. That's going to be 5. Choose 1. 5 factorial. 5 minus 1 factorial. 1 factorial. And don't forget, 1 factorial also equals 1. This becomes 5 factorial. 5 minus 1 factorial, that's 4 factorial. 4 factorial in the denominator will factor out 4 factorial in the numerator, leaving us with 5, which again, we figured that logically. For C has how many different types of pizza can a student order with 2 toppings? You could even do this without the formula. We can say we could do a green pepper and a black olive. We can do a green pepper and onion. We can do green pepper and pepperoni. We can do green pepper and tomato. We can do black olive and onion, black olive and pepperoni, black olive and tomato, onion and pepperoni, onion and tomato, or pepperoni and tomato. We figured out some counting techniques earlier just by doing it through a tree diagram or doing it logically that way. So that's the same thing. But we'll go ahead and use the formula here. N, choose R. That's going to be 5, choose 2. 5 factorial. 5 minus 2 factorial times 2 factorial. That becomes 5 factorial. 5 minus 2 factorial, that's 3 factorial. 2 factorial. And if you look at this, this looks just like those non-distinct examples that we were doing earlier. 3 factorial is going to factor out 3 factorial in our numerator, leaving us with 5 times 4. 2 factorial is 2. 5 times 4 is 20, divided by 2. That's 10. And I think we counted off 10 when we were doing it this way, using a little tree diagram. So there's 10. And for letter D, it says, how many different types of pizzas can a student order with no more than 3 toppings? Here we have no more than 3 toppings. Well, what does no more than 3 mean? Well, I guess that means 3 or less. 3 toppings, 2 toppings, 1 topping, or no toppings. So we already figured out what it is for 2 toppings right here. Here it is for 1. Here it is for none. So let's just find out what it is for 3 toppings. So we have N, choose R. 5, choose 3. 5 factorial. 5 minus 3 factorial. 3 factorial. That's 5 factorial. 5 minus 3 factorial, that's 2 factorial. 3 factorial. And this looks just like this. So 5 choose 2 is also equal to 10. So there are 10 different ways that we can order it with 3 toppings. So if there's 10 for 3 toppings, 10 for 2 toppings, 5 for 1 topping, and 1 for no toppings, then how many different types of pizzas can a student order with no more than 3 toppings? We just add them all together, and it's 26. And there we have it.